Hello everyone, welcome to this lecture on Gershgorin theorem, and this theorem is useful to locate the eigenvalues of a matrix. Let us discuss the main idea about this theorem. Let lambda be an eigenvalue of matrix A, 3 by 3 matrix, square matrix A with eigenvector capital X, and definitely eigenvector is always non-zero. Then by the definition of eigenvalue and eigenvector, we can write Ax equal to lambda x. It means multiplying A with vector capital X scales the vector x by scalar lambda. So this is the matrix equation, and applying row-wise multiplication, we get these three equations. In first equation, you can see right side we have lambda x1. In second equation, we have lambda x2. In third equation, we have lambda x3. Now we consider an important idea. What is the idea? This eigenvector has three components. Okay, x1, x2, x3. We take the modulus of x1, modulus of x2, modulus of x3. Okay, so among these three numbers, modulus of x1, modulus of x2, and modulus of x3, at least one must be maximum. Okay, so we consider three cases based on that, and in first case we assume that modulus of x1 is maximum. Okay, it means that modulus of x1 is greater than or equal to modulus of x2. It is also greater than or equal to modulus of x3. It means x1 has maximum magnitude. Okay, you can see here that as row 1 contains x1 on the right hand side, here we have lambda x1. So we take the first equation, we proceed with first equation here. This is the first equation. We rearrange the terms. So we can write here, you can see lambda minus a11 x1, a12 x2 plus a13 x3. Now taking modulus of both sides. So modulus of lambda minus a11 into modulus of x1 equal to modulus of this term, modulus a12 x2 plus modulus a13 x3. Now here we apply triangle inequality. What is triangular inequality? Means suppose we have two vectors x plus y, so we can write modulus of x plus y less than equal to modulus of x plus modulus of y. So using triangular inequality, we can write here modulus of this plus this less than equal to modulus of this one plus modulus of this one. Clear? Now using the maximum property, as modulus of x1 is maximum of modulus of x2, and it is maximum greater than or equal to the modulus of x3. So we replace modulus of x2 and modulus of x3 by modulus of x1. So we can write it is less than or equal to this plus this into modulus of x1. Now we have modulus of x1 in both sides, so we cancel modulus of x1, modulus of x1. So what we are getting? Modulus of lambda minus a11 less than or equal to modulus of a11 plus modulus of a13. And we say this sum is R1. Okay. So you can see here this inequality, this inequality represents a disk in the complex plane with center a11 and radius r1. Okay, So we denote this disk by C1, and you can see here also this is C1, and this is the center of this disk, and this is the radius. This disk contains the complex numbers. Z contains the points whose distance from the center is less than or equal to its radius, means less than or equal to r1. And important thing is that this lambda satisfies this inequality, means lambda, which is eigenvalue, lies inside the disk. So you can see here, this is the lambda which is inside the disk. So now we consider second case. Second case is modulus of x2 is maximum. Now we check. So you can see here x2 we have in second equation. So we start with second equation. And again we rearrange the terms, taking absolute on both sides, using the maximum property, we get this inequality. Okay. So you can see here, this gives the second disk that we denote by C2. Okay. With center A22 and radius R2. Okay. This is the second disk. Center is A22 and this is the radius, and lambda is inside this disk C2. Now third case, we assume modulus of x3 is maximum. So after applying the similar procedure, we start with the third equation. As in third equation we have x3, so we start with this third equation and applying the same procedure, we get this inequality. So this inequality represents a disk with center A33 and radius R3, and clearly this lambda eigenvalue satisfies this inequality. It means lambda is inside the disk. So this inequality represents a disk, and we denote this disk by C3. And you can see here this lambda is inside this disk. So finally what we conclude, since one of these three cases must always occur, so we can say every eigenvalue lambda satisfies at least one of these three inequalities, either this one or this one or this one. Okay, so every eigenvalue of matrix A lies inside at least one of the three disks C1, C2 and C3. Now let us state the main theorem, Gershgorin theorem. So let A be an n-cross n square matrix. So we define this theorem with respect to rows. So for each row I, we define Gershgorin disk that we denote by Ci, and it is defined as set of all complex numbers satisfying this inequality. In this inequality, this A11, Aii is the diagonal element of the matrix. And what is Ri? It is defined as absolute values of non-diagonal entries, non-diagonal elements. So we can write here, it is a modulus of A12 plus modulus of A13 plus and so on modulus of A1n. Okay. So as we define Ci, Gershgorin disk Ci for each row I. So how many rows here we have? we have n rows here for matrix A. So how many disks we have here? N disks. Means we will have C1, C2, C3 up to Cn. So this theorem says that every eigenvalue of A lies in at least one of the disks Ci. Means eigenvalue lies in at least one of the disks C1 or C2 or C3 or C1. Okay. So in other words, we can say all eigenvalues of A lie in the union of the disks Ci. Means lambda belongs to C1 union C2 union C3 and so on union Cn. This is the diagram. So you can see this is the disk Ci with center AII, which is diagonal elements of the matrix, and this is the radius Ri, which is defined as absolute values of non-diagonal elements, and this is the eigenvalue which is inside this disk. So finally we write the statement of this theorem. Every eigenvalue of a matrix A lies inside at least one Gershgorin disk formed from its rows or columns. This theorem we have defined with respect to rows. This theorem can be defined with respect to columns also in the similar way. Now let us see why this theorem is useful. So here we are going to discuss some important points. First is we can locate the eigenvalues quickly in complex plane without solving complicated equations. As we know that eigenvalues and eigenvectors of a matrix are evaluated using the characteristic equations, but characteristic equations may be complicated. Okay, so to locate the eigenvalues, to know the bounds of eigenvalues, we use this theorem. Second is a separate disk contains exactly one eigenvalue. Okay, means if a disk does not overlap with others, it contains exactly one eigenvalue. So you can see here, this is the separate disk. So definitely it will have exactly one eigenvalue only. Cluster of k disks implies exactly k eigenvalues. So you can see the diagram here. Here we have these three disks. So if k disks overlap together, then that region contains exactly k eigenvalues. Okay, so eigenvalues may be in this region. Next point is if 0 is outside all disks, okay, then matrix is non-singular or invertible. So you can see here this is the 0 and this 0 is outside all disks. So definitely these disks we are getting corresponding to some matrix and that matrix will be non-singular. Now let us take an example. Example is draw the Gershgorin disks for the following matrix. Okay. So we start with first row. In first row you see this is A11 diagonal entry, this is non-diagonal entry A12, this is A13. Okay, so here center is diagonal entry, this one 4. Now we find the radius. Radius is the sum of absolute values of non-diagonal entries. So absolute value of this one is modulus of -1. So we are getting 1, and for this one modulus of 0 it is 1. So we are getting R1 1, radius 1. So disk we are getting C1 with center 4 A11 and 1 and radius 1. 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 And radius 1 So disk is shown in this diagram. You can see here, this is the center 4 and radius is 1. So 4 to 5 1. You can see here, this is the radius. Now corresponding to second row. In second row, A22 is 3. You can see here. So center will be 3 and radius is the sum of uh, modulus of non-diagonal entries. So modulus of 2 is 2, modulus of 1 is 1. So we are getting 3 here. So we are so corresponding to second row, we are getting this disk C2 with centers 3 and radius 3. So in this diagram you can see center is 3 and radius also is 3. You can see here 1 2 3. Okay. Now corresponding to third row of this matrix, we are getting another disk with center 5. So this is A11, this is A22 actually. This is A33. So A33 is 5 and radius will be absolute values of non-diagonal elements 0 and for absolute value of minus 2 it is 2. So we are getting here 2. So now we are getting disk C3 with center 5 and radius 2. So you can see here center is 5 and radius is 2. So thank you for watching this video. If you found this lecture helpful, you can like, subscribe and share this video. And if you have any doubt or questions, then you can write them in the comment section.